In this video, we'll be looking at a Leaving Certificate physics experiment to verify the principle of conservation of momentum. But first, what is momentum? Simply put, momentum is mass times velocity. We denote momentum with the symbol p, so we have p equals m times v. As mass has units of kilogram and velocity has units of meters per second, it follows that the unit of momentum is kilogram meters per second. It is important to note that we are using velocity and not speed, as speed is a scalar quantity and has only magnitude, whereas velocity is a vector quantity that has magnitude and direction. For example, you could say the speed of the car is 50 kilometers per hour, but the velocity of the car is 50 kilometers per hour north. It follows then that momentum is a vector quantity that takes its direction from the velocity. The principle of conservation of momentum states that if no external forces act on a system, the total momentum of the system cannot change. This means that for any interaction between two bodies, as long as there are no external forces acting on the system, the momentum before the interaction will be equal to the momentum after the interaction. We can express this with the mathematical formula below, noting that u is the initial velocity, whereas v is the final velocity, and the subscripts denote which body we are referring to. So for example, m1u1 is the momentum of body 1 before the collision, whereas m2v2 is the momentum of body 2 after the collision. A completely inelastic collision is one where the bodies stick together. It follows then that after the collision the velocity of body 1 and the velocity of body 2 will be equal. This allows us to simplify the equation on the right hand side as follows. Note that depending on your school you may use different apparatus than shown in this experiment. The apparatus includes an air blower and an air track, two metal riders, one with a flag that measures 0.1 meters long and both with pieces of Velcro on the ends facing each other to ensure an inelastic collision. The riders have an upside down V shape that allows them to sit securely on the air track. Finally, we have a pair of retort stands which hold the light gates above the air track, which are in turn connected to the scalar timers. The air track is a long rigid tube with small holes along its upper faces. It measures 180 centimeters in length. It is connected to the air blower with a hose, and when the air blower is turned on, it forces a continuous airflow through the holes of the air track. This lifts the rider just off the track so as it's floating on a thin cushion of air, removing nearly all friction between the glider and the track. Next, let's look at the light gate. The light gate consists of a light emitting diode on one side and a photodiode on the other side. The light emitting diode shines a beam of light onto the photodiode, represented in this animation as a green laser. As the glider passes under the light gate, its flag breaks the beam of light. This sends an electrical signal to the scalar timer, which in turn starts the timer. The timer stops once the flag is no longer breaking the beam of light. As velocity is equal to displacement over time, we can now calculate the velocity of the glider. With the displacement being equal to the length of the flag, and taking our time from the scalar timer, we can calculate u1, or the velocity of rider 1 before the collision. Using standard units, this means we have 0.1 meters divided by 3.37 seconds, giving us 0.03 meters per second. Remember to reset the timer before each use. The track should be leveled using the leveling screws at either end of the air track. To ensure that the track is level, we move one of the riders to the center of the track. If the rider moves to the left, the start of the track needs to be raised. If it moves to the right, then the start of the track needs to be lowered. Finally, we can move the rider back to the start of the track and give it a gentle push. As the timers are equal, we can conclude that our rider is moving with constant velocity and that our track is level. For our first experiment, place rider 1 with the flag at the start of the track and rider 2 without the flag in the middle of the track, and give rider 1 a gentle push. In this first experiment, both riders have mass of 0.25 kilograms. Now, as before, we can calculate the velocity of rider 1 before the collision and of the two riders after the collision. We can now record our values in a table. m1 and m2 both equal 0.25 kilograms. u1 is 0.33 meters per second, while u2 is 0 meters per second, and v is equal to 0.16 meters per second. Now, writing down our formula for the conservation momentum, we can simply fill in the variables. Solving both sides of the equation, we get nearly identical values. The difference in values could be due to a number of reasons, such as friction on the track or due to rounding errors. For our next experiment, we'll place rider 2 with a 1 kg rider. This time we can see after the collision they move together much slower. As before, we calculate our velocities using the scalar timers. Once again, writing down our variables, we can put them into the equation for conservation of momentum and see if momentum has been conserved. As we can see, both sides of the equation are equal, and even though we change the mass of rider 2, momentum has still been conserved. For this next experiment, we'll do a head-on collision of the two riders. Notice this time that they both have flags, as we are measuring both their velocities independent of each other. It is not important that the riders start at different distances from the light gates. However, it is important to release the riders before the light gates, otherwise your hand may still be accelerating the riders and you will not be measuring constant velocity. In this experiment, it is important to remember that momentum is a vector quantity. Let's define movement to the right as positive and movement to the left as negative. Now, with the help of a classmate, push the riders towards each other with equal force. Here we can see that as time is equal, speed will also be equal. But note that as rider 2 is moving in the negative direction, it has a negative velocity. Once again, recording our values and putting them into the equation, making sure to note that we have negative values this time in the equation, we can see that the conservation momentum has still been conserved, and that is independent of direction. But now you might be thinking, what happens if they don't stick? Well, we call these elastic collisions. For our final experiment, we'll be looking at a completely elastic collision. To simplify calculations, we'll be using a black rider of 1 kg and a blue rider of 2 kg. You'll notice a thin metal ring at the end of the black rider. This acts like a spring and ensures an elastic collision between the two riders. It is important to pay attention to the first scalar timer, as it will be recording 2 separate times. In case you missed it, the first scalar timer initially recorded 0.10 seconds, allowing us to calculate u1, the initial velocity of rider 1. The first scalar timer then recorded rider 1 on its way back, with a total time measuring 0.40 seconds. By subtracting the initial time of 0.10 seconds from the final time of 0.40 seconds, we can calculate the final velocity of rider 1. Also note that as it was moving to the left this time, it has a negative velocity. Once again, we write down the values from our experiment. This time we'll use the full equation for the conservation of momentum, as the final velocities are different. Putting our values into the equation and paying special attention that the final velocity of rider 1 is negative, we can easily see that both sides of the equation equate to 1 kg meter per second. In summary, we completed 4 trials under different circumstances, and using our equation for the conservation of momentum, we were able to show that in each case, as long as there were no external forces acting on the system, that momentum was conserved within the limits of experimental error. Thank you for watching, and I hope this video has been of help to you.